In the previous module, we have derived the equation for the Fourier series representation of discrete time periodic signals, and the equations that we have obtained are shown on the screen. Let us take an example. Consider a signal shown on the screen. The signal shown on the screen, as you can see, is a kind of square wave that repeats after 10 samples. You can see that this entity here, this square wave, repeats after 10 samples. So this period of the signal is n0 equals to 10, and if we know n0, we can know what is omega naught, that is the fundamental period of the discrete time periodic signals. So this small omega naught is going to be 2 pi by n0, that is going to be pi by 5. Now that we know this omega naught, we can calculate this AKs. So these AKs are going to be equals to 1 upon n0, that is 1 upon 10 summation over a period. Now this period is over this small n in any period of n0. That means I can take any range of this n0. So the range of n0 could be from 0 to 9. So that makes 10 samples. I may take from 1 to 11. I may take the range from 2 to 12 and so on. So any range of small n is fine as long as it covers all n0 samples. So I'm deliberately choosing the range from, let's say, from -4 to 5. So from -4 to 5 also it makes me 10 samples. So -4 is one sample, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 there. So I'm deliberately choosing this range from -4 to 5. So what is the advantage there? I'm going to get this once in continuum. So I need not take two different sets of the summation. So that's why I've chosen this range of small n from -4 to 5. No matter what range you choose, as long as it covers n0 samples, it is going to give you the same answer. So I'm choosing the range of this small n, let's say from -4 to 5. That is going to be x of n, and we know what is x of n, that is 1 e power minus jk. Small omega naught is pi by 5 times n. So this is going to be equals to, now we know that from -4 to 5, the samples that are non-zero are from -3 to 3. So this signal, and of course x of n, so I've not written x of n there. So this is going to be x of n e power minus jk. Omega naught is pi by 5 times n, and as we know that this x of n is finite over the -3 to 3, so I will write it from summation n equals to from -3 to 3, and we know what is that x of n. You can see from -4 to 5, this sample -4, and at 4, 5 they are 0, and for rest of the values it is 1. So that is 1 e power minus jk pi by 5 times n. So this is going to be equals to, now if I make a change of variable here, I am making a change of variable of n here. So what I'm going to write here is, now that is for convenience, for mathematical convenience, I'm writing this change of variable, that is n plus 3. I'm writing it as small m, so that I can start this summation from 0. You can see that if n is -3, that m becomes 0. So this equation turns out to be equals to (1 upon 10). This summation now is from m equals to 0 to 6 e power minus jk pi by 5 times, now the small n is going to be m minus 3, So this is going to be equals to 1 upon 10. I'll take this e power plus jk 3 pi by 5 common outside the summation, and we are going to get summation m equals to 0 to 6. I'll write this in different form. It is going to be e power minus jk 3 pi by 5 is already taken common, so we are left with m pi by 5. So I'll write that as k pi by 5 and whole to the power m. Now this is kind of limited summation, and we know what is the formula for that. So on the next page I'll write it as these ek's are going to be 1 upon 10 e power minus the plus j 3 pi by 5 times 1 minus e power, you can see that this is going to be e power minus jk pi by 5 minus jk pi by 5 upon, so just multiplied by 7, because the total number of samples is from -3 to 3, or you can say from 0 to 6, so that is going to be 7 divided by, so let me write this again, so this is going to be 1 minus e power minus j k by 5 k pi by 5 times 7. So this into 7 to the power 7 divided by 1 minus e power minus jk pi by 5. Now that is going to be, now this is 7 pi by 5 k 7 pi by 5, and I'm taking half of this power common, so you'll come to know why I'm doing that. So for simplification, what I'm doing here is 1 upon 10 e power jk 3 pi by 5 was already there. Now I'm taking half of this power outside this bracket. What I mean to say is I'm taking e power minus jk. Now we already have here 7 pi by 5, so instead of that, half of that would give you 7 pi by 10. I'm taking that common, 7 pi by 10. So in bracket what we have is e power plus jk 7 pi by 10 minus e to the power minus j k 7 pi by 10. Now you would appreciate why I've done that, because I need to make this as complex exponential minus e power, the complex conjugate of this complex exponential. If you can represent in this form, I can express that in terms of sign, so that's why I've taken this term common. Similarly in the denominator, so in the denominator we are going to get e power, I'm taking half of the power of the complex exponential common, so minus jk pi by 10 I'm taking common, so that is going to give you e power plus jk pi by 10 minus e power minus jk pi by 10. Now we can see that this one here is going to give you, this is 3 pi by 5, that means 6 pi by 10, and if this goes up, that is going to be 7 pi by 10, So e power minus jk 7 pi by 10 and e power jk plus 7 pi by 10 is going to get cancelled, and what we are left with is equals to 1 upon 10. All the exponentials get cancelled, and what we are going to get is sine k times 7 pi by 10 divided by sine k pi by 10. That is the final expression for a k. Let's stop here.